Hey everyone, I'm here to teach you your next lesson. We are going to be in Chapter 9, Lesson 6. This is our last lesson from Chapter 9. It's on permutations, and you're going to need pages 768 and 769 from your math book or the math packets. Or if you do not have either of those, you can follow along using notebook paper. You'll need pencil, and you will definitely want a calculator today. Okay? To start with, permutations is a fancy math word that has to do with listing or organizing different objects or things in a specific order, okay? So when we do today's lesson, we're going to be thinking about the things that we've already learned. We're going to be thinking in terms of sample space, all the different combinations that we can make of possible outcomes in a set situation. And we're going to also be using what we've learned about the fundamental counting principle that says you can use multiplication to help you quickly get to the number of possible outcomes in a given situation without having to list the entire sample space. We know listing that sample space is not too big of a deal if you only have 6, maybe 8 outcomes. But if you've got 3,024, that's kind of ridiculous. So you would want to be able to use math, use numbers to figure that out. So a permutation, again, by my math book, it's defined as an arrangement, a listing, or an organized format for placing objects in a specific order, okay? Now, right now, that still probably doesn't make much sense to you, but I have 4 different examples that I'm going to do with you before we start the math lesson to actually give you an idea of what we mean by this. All right, so the first one, I've used whiteboards to kind of set these up. I got 3 kids, y'all know that, Carson, Cy, and Will. Let's say that I'm going to have pictures made of my kids. And I need to figure out the way that I want to have them lined up for their photographs. Okay? So I want to know all the different ways that I could position my children in a row for the different possibilities for having their picture made. So let me kind of just talk you through this one in terms of what a permutation might look like. I'll try to scoot over and show you this. So, okay, I could take and I could do Carson, Cy, and then Will. I could do Carson, Will, then Cy. I could do Cy, then Carson, then Will. Cy, Will, Carson. I could do Will, then Carson, then Cy. Will, Cy, then Carson. This should feel very much like a review from sample space, okay? So there are 6 different combinations, different ways that I could organize or list these 3 children in a specific order, okay? So we're thinking along the lines of sample space, all the different ways I could combine them, okay? Now let me show you how I can use the fundamental counting principle to figure this out also, okay? Because I have 3 different children, okay? And because after I place one child in the first position, there will only be 2 positions left, or 2 possibilities. I could multiply that times 2. And then once I place a child in the first position and a child in the second position, that means there's only going to be 1 option left for the third position. Okay, so let me explain again what this means. The first position, I have 3 options, Carson, Cy, or Will. Once I've placed one of those in the first position, I then have 2 other options for the second position. Once I've placed both the first and second child in place, I'm only going to have 1 option for the third position. I can use the fundamental counting principle. I can multiply all of these together. 3 times 2 times 1 is 6. So there are 6 different possible ways I could line my children up for photographs. Okay? Now, let me show you another one. We've got the word math. I want to know, in this example problem, what is the probability of me randomly, let me see how the example problem was listed right here, because I really like the way they did it. That's why I had chosen to use this one. Okay, they say 2 different letters are randomly selected from the letters in the word math. What is the probability that the first letter selected is M, and you can see I've underlined it here, and the second letter is H? Well, we know that probability, we have to first of all know our number of possible outcomes, okay? So what we need to know is we need to know all the different ways that we could possibly draw 2 letters out from this, these 4 letters, this 4-letter word, okay? So here's what we would need to start with first. We know we're focusing on drawing 2 letters. The first letter, the second letter. So here's a little trick, a little hint. So we're going to do 2 different trials 2 different times. Now, the first time I draw a letter, I have 4 different possibilities that I could draw. The second time that I draw a letter, I'm only going to have 3 of those letters left. So I would use the fundamental counting principle, and I would do 4 times 3 to know that there are a total of 12 possible outcomes. Now, there is only going to be one unique combination of me being able to pull an M and then an H. So that would be a 1 in 12 chance, which you could then convert to a percentage to get a percentage chance also. Okay? Let's look at the next example. In your book, we're going to see this a couple times, and I wanted to introduce to you, kind of let you know how to recognize it. We know that this P outside of the parentheses represents the probability, okay? And inside the parentheses here, we have an 8 and a 2. What this is asking us is, what is the probability if we have 8 things in our situation, so 8 people, 8 different sandwich meats, 8 different shirts, whatever it may be. So 8 different outcomes. And if we choose from those 2 different times, what is the probability, or how many different outcomes could there possibly be? So here's how we figure that out. We want to first of all say, okay, we're going to choose 2 different times. So we're going to do 2 little trials here of 2 different times. The first time, we're going to have 8 possibilities. The second time, because we've already done 1, there will only be 7 left. So we would say that there are 56 different possible arrangements in this specific situation. Okay, now we don't know what this 8 represents. It doesn't matter. But if we have 8 things and we're going to pull 2 different times, there's 56 different possible ways that could happen with 8 different items. Okay? Last one. Use a little bit larger number here. Let's say that you go to an ice cream shop and they have 31 different ice cream flavors there. And your grown-up says, you know what? We're going to really splurge today. You're going to get the 3-scoop cone. But here's the kicker. You can't get any of the same 3 flavors. We're going to branch out. We're going to try something different. So you can't do 3 chocolates. You can't do 2 chocolates and a vanilla. You got to do 3 different flavors. Now, I want to know if there's 31 ice cream flavors there. And we want to figure out how many possible different ways we could arrange these 31 ice cream flavors into a 3-scoop cone. How many would it be? What would we do here? Okay, so here's what I do. I start with this 3. I need to say to myself, okay, how many different times am I going to put a scoop of ice cream out? Well, I'm going to put it out 3 different times into that cone. So that kind of lets you know how many blanks to draw there. And this is just a Miss McGowan strategy. Now, on the first scoop, you've got 31 choices. But on that second scoop, because you've already used 1, now you're only going to have 30 choices for the second scoop. And because you've already used 1 choice for the first scoop and 1 choice for the second scoop, now for your final scoop, there's only 29 choices left. So we would use the fundamental counting principle. I've got my calculator right here. And we would multiply 31 times 30 times 29. And we get a whopping 26,970 different ways that you could stack 3 different scoops of ice cream out of those 31 flavors, okay? So there would be, any one unique combination would be a 1 in 26,970 chance. Teeny tiny percentage there, okay? So permutations, one more time before we get ready to do our book work, has to do with all the different ways we can arrange, line up, or organize the different objects in a set, okay? This can be people lining up for a photograph. This can be ice cream flavors getting stacked in a 3-scoop cone. This can be randomly pulling 2 letters from a 4-letter word. There's just millions of different ways this can be thought of. But what you want to think of is, first of all, how many times am I pulling something? Or how many times or ways am I wanting to arrange it? And then start with your first time. There's X number of outcomes. Your second time, there's going to be 1 less than that. Your third time, 1 less than that, and so on and so forth. We're going to look at examples where there's multiple times that we're pulling that out. So I'm going to pause the video and I'm going to get myself set up. You guys need 768, 769 from the book or packets or notebook paper. Get you a pencil, and you definitely want your calculator. Okay, see you in just a minute. Okay, kiddos, we're back and we're on page 768, and we're going to practice some problems now together with all of the different possible ways or the permutations that could involve a given number of objects in a specific set. So how the different ways we could list them or arrange them in a specific order. We're going to use our fundamental counting principle, which says we can multiply to find the number of outcomes possible. So number 1 says, in how many ways can a president, vice president, and secretary be randomly selected from a class of 25 students? Now here's the strategy I want to offer you. I want you to start by asking yourself, how many different times are we going to have to choose a person to fill the role of president, vice president, and secretary? Well, there's 1 president, 1 vice president, and 1 secretary. So that means there are 3 different times that we're going to have to choose a student for those roles. Now, to find the total different number of outcomes possible with 25 students, what we would say is, okay, the first time I choose a student officer, I'm going to have 25 different students to choose from. But once a student has been chosen for president, he can't serve as vice president or secretary. So the next time, I'm going to be down to only 24 choices. Well, once a student is serving as vice president or president, they're not eligible to choose to serve as the secretary. So now I only have the remaining 23 students. This is where we can use multiplication. So you'll want to get your calculator. And we'll do 25 times 24 times 23. And we can see that there are 13,800 different combinations of president, vice president, and secretary out of 25 students. Number two wants us to find the value of the permutation or the probability of order and listing of 5 different things taken out 3 times. Going back to my example, when you see this listed, this means 5 different things 3 different times. So it could be 5 different people. It could be 5 different ice cream flavors. It could be a 5-letter word. And we're focusing on 3 different times that we're going to pull from that. Okay, so relating it to the first example, it would be like a group of 5 students with 3 different offices of president, vice president, and secretary, just to kind of help you understand how this is presented to you. So because we're going to do 3 different times, I can go ahead and set that up like that. Now the first time, I'm going to have 5 different options. But then the second time, because I've already used 1, there will only be 4 left. And the third time, because I've already used 2, there will only be 3 left. Now, I can mentally do this math. I know that 5 times 4 is 20, and 20 times 3 is 60. So there would be 60 possible outcomes with 5 different objects pulled 3 different times. Okay? Now, number 3 is focusing on the probability of an event happening using the same way of thinking. It says Adrian, Julian, and 2 of their friends will sit in a row at a baseball game. If each friend is equally likely to sit in any seat, what is the probability that Adrian will sit in the first seat and Julian will sit in the second seat? Okay? So, on this one, what we're focusing on here is the probability of, if we have 1, 2 people plus 2 more friends, 4 different people, and 2 different seats, the first seat and the second seat, okay? So that's kind of presenting it to you the way it was done in number 2. We want to know the different ways that these 4 people could possibly be positioned to sit in the first seat and the second seat at the baseball game. So we know we're going to do this 2 times. That's going to represent the first seat. That's going to represent the second seat. Now, for the first seat, you've got 4 friends available. But once someone sits in that first seat, there's only 3 different options left for that second seat. So we would do 4 times 3, which gives us 12 different possible outcomes. Now in this question, our answer is not just 12 because it says, what is the probability that Adrian will be in the first seat and Julian would be in the second seat? That's going to be one unique combination, okay, of 2 specific people sitting in this first and second seat. So because it's one unique combination, we would say that there is a 1 in 12 chance. And if we wanted to convert that in to a percentage, because we know probability is often given to that, we would say that there is about an 8% chance of that happening. Okay? Let's move on to 769. On 769, number 1 says, in the Battle of the Bands contest, in how many ways can the 4 participating bands perform? Okay, so on this specific question, we know that we have 4 different bands. So obviously there's going to be 4 different performances. So you might see this set up like this. The probability or the number of outcomes or permutations for 4 different bands where there's 4 different performances. Okay, so we know we're going to start with our 4 different performances. Performance 1, performance 2, performance 3, performance 4. Now, for the first performance, you've got 4 different bands to choose from. So you have 4 options there. But once a band has performed, they're no longer in the mix of things. So now the second performance, you're going to have 3 different possible bands left. The third performance, because you've already had 2 perform, now you only have 2 bands left. And for your final performance, it's going to be the 1 remaining band, okay? So we know that 4 times 3 is 12, times 2 is 24, times 1 is still 24. So there's 24 different ways, 24 different combinations, 24 different possible outcomes or permutations that would allow these bands to perform in different ways or different orders. Number 2, a garage door code has 5 digits. If no 1 digit is repeated, how many codes are possible? Now, when you think of this, when you think of a garage door code, we know that there's going to be 5 different digits, okay? So we know that we're going to have 5 different times that we have to choose a number. But the number of possible outcomes, if you think about it, there's 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. So that actually makes 10 different numbers that could be chosen each of those 5 times because we have to include 0. So 5 different numbers, and it says they cannot be repeated. That's the kicker here. They can't be repeated. So for our first number, we have 10 different options, 0 through 9. But once one of those numbers has been chosen for the first digit, you're only going to have 9 left for the second one. Then you'll only have 8 left. Then you'll have 7 left. And then for your 5th and final digit, because you've already used 4, there will only be 6 digits left that could possibly be that last number in the code. Now, we'll want to use our calculator for this one. I know that 10 times 9 is 90, times 8 times 7 times 6 gives me 30,240 different possibilities for a passcode for that garage door. Okay? Find each value. Use a calculator if needed. So on these, we know that this means how many different permutations, outcomes, possible ways that we could take 7 objects and arrange them 4 ways, basically, okay? Or 4 different times. 7 objects pulled 4 different times. How many different ways could we do that, okay? So we're going to start with the 4 different times. We know the first time that there will be 7 objects to choose from. The second time, there will only be 6. The third time, there will only be 5. And then finally, there will be 4 left for that last time. We would do 7 times 6 times 5 times 4, which gives us 840 different permutations or ways that these 7 different objects could be organized in groups of 4. All right, number 4, same thing. Now we have 12 objects that we're going to take out 5 times. So we're going to do 5 different times that we take it out. We know the first time, because there's 12 objects, there will be 12 objects to choose from. The next time there will only be 11. The next time there will only be 10 because we've already chosen one for the first and second. Then there will only be 9, and then there will only be 8. Each time, you should be catching on to this, there's going to be 1 less outcome possible than the time before that. So let's take our calculators. And we get 95,040 different ways. Those 12 different objects could be organized or listed, pulling 5 at a time. All right, and then the last one here, 8 objects, 8 times. So we're gonna do 1, I'm gonna try to write small on this one, 3, 4, 5, 6, 7, 8. Okay, so we have 8 objects. We're going to pull 8 different times. So the first time I'll have 8 options, then I'll have 7, and I'm just going to work my way down until the last time there will only be one of those objects left. So we would just use our calculators here. Whoops. And we get 40,320 different ways those 8 objects could be organized. Okay? 2 more. Number 6. You have 5 seasons of your favorite TV show on DVD. If you randomly select 2 of them from a shelf, what is the probability that you will select season 1 first and season 2 second? So when we think of it this way, we have 5 objects. In this situation, it's 5 seasons of a TV show. And we want to know the probability of choosing a specific one for the first season and the second season. So that's 2 different times that we're going to choose a DVD. Okay? So 5 different seasons. We're going to choose 2, take out 2 times. Okay? So we know that the first time there's going to be 5 seasons to choose from randomly on that shelf. But the second time there will only be 4 left. So we know that there are a total of 20 different possible ways that could happen. Now it said what is the probability that you would get season 1 first and season 2 second. That is a unique combination. So we would say that there is a 1 in 20 chance. And if you wanted to show that as a percentage, it would be about a 5% chance of that unique combination being chosen. Okay? The fewer objects there are, the higher the chances are of a specific unique combination happening. The more possible outcomes there are, like for example in this one or this one, obviously it's going to be a very minute, small chance of a unique combination being chosen. Last one, number 7, says the graphic novel frame below explains how the survey has students rank their favorite kinds of music and how many ways can the survey be answered. So the kids here are saying, okay, we're going to ask teens to place a 1, 2, 3, 4, or 5 next to each type of music. Okay, so they're going to rate them 5 different ways as either a 1, 2, 3, 4, 5. Over here, she says, okay, our list is going to include country music, classical music, hip hop, oldies, and alternative. So that's 5 different types of music, or 5 different objects. In this sense, it's a genre of music. And we're going to rate them 5 different ways. Okay? So when we think of it that way, they're going to rate all 5 genres of music as either a 1, 2, 3, 4, 5. They're going to order them based on their opinion of what's the best down to what's their least favorite, okay? So on their first option, let's just say the one that they're going to give a 5 to, they're going to have 5 different genres to choose from. But once they have rated that one, then they're only going to have 4 left. Then they're only going to have 3 left. And then they're going to be down to their last 2 genres of music that they're going to give, let's just say, a 2 and a 1 to. Okay? And then once they've done those, there will be the final one remaining. Okay? So when we use our fundamental counting principle here, we can do 5 times 4 times 3 times 2 times 1. And we get 120 different ways that the kids could possibly rate those 5 different genres of music. Okay? Now, what I'm going to do is I'm going to end the video and I'm going to go make you guys an answer key for the extra practice page. These are not required, but I really encourage you guys, if you're really trying to do this thing right, this distance learning right, after we do the lessons together, go try the extra practice pages. This one's going to be page 771. Try it on your own, and then I will send you guys the answer key so that you can self-check to see how you're doing, okay? I appreciate all the work you guys are sending back. You've exceeded my expectations. I miss you, and I'll see you next time. Thanks, guys.